Another long, strenuous problem, but some pretty cool results. The statement reads, for A, another way to fill this missing link we talked about in the last question is to look for a magnetostatic analog to the electric potential, and the obvious candidate would be A as a function of R is equal to the integral B cross dl from some origin to R. Test this formula for the simplest possible case, a uniform magnetic field. Use the origin as your reference point. Is the result consistent with A of R is equal to negative 1/2 R cross B? You could cure this problem by throwing in a factor of 1/2, but the flaw in the equation runs deeper. Alright, part 2. For B, we need to show that this integral B cross dl is not independent of path. By calculating the closed integral around the rectangular loop shown in the diagram, and as far as I know, the best that one can do along these lines is the pair of equations V of R is equal to negative R dotted with the integral of E as a function of lambda R d lambda, and similarly A but with lambda B of lambda R d lambda. So some kind of parameterization of it. And then C or use equation 2 to find the vector potential for a uniform magnetic field, and D use equation 2 to find the vector potential of an infinite solenoid or an infinite straight wire carrying a steady current I. Does equation 2 automatically satisfy the divergence of A equals 0? That was a mouthful, so let's go look at the diagram. We just have a quick rectangular loop, like they said, a separation distance A to B from one to the other. All right, length W, steady current I. No biggie there. All right, for part A, we have for a uniform magnetic field B, this integral says that we need B cross dl, but the magnetic field is uniform, so we can pull that outside of the integral and just take the cross product with the integral of dl, which we know is the vector R, but that does not equal A of R equal negative 1/2 R cross B. The negative could come from the fact that the cross products are anti-symmetric, or anti-commutative rather, so we switch the order, put a negative on it. And then B, we know that for a straight wire, the magnetic field is mu naught I over 2 pi s. So evaluating the closed integral B cross dl, we end up with mu naught I over 2 pi a s hat minus mu naught I over 2 pi b s hat times w. All right, fair enough. Factor the mu naught I over 2 pi out. You're left with 1 over a minus 1 over b s hat, but that, again, does not equal 0. C, for the uniform magnetic field, A of R is equal to negative R cross the integral lambda b lambda R d lambda. Okay, again, magnetic field uniform, pull it out, and we see here that we have negative R cross B, integral from 0 to 1 of lambda d lambda, which again, power rule gives you that factor of 1/2. Good to go there, that checks out. For D, however, B is equal to mu naught I over 2 pi s phi hat, so when we put the fact that this is a function of lambda R, we just have to put a lambda on the s as well. All right, so go ahead and plug that in. We see that the lambda cancels with the lambda. Since it is a constant, we pulled it out. And that whole integral goes to 1, leaving us with negative mu naught I over 2 pi s R vector cross phi hat. But here, R is the vector from the origin, and cylindrical coordinates would be represented as s hat plus z hat, right? Because the cross product of a vector in itself is 0, so it doesn't pay to incorporate the phi hat. All right, whatever. So next we see that A equal negative mu naught I 2 pi s with the cross product, so we just distribute that, factored out the constant s and z respectively, and now we know that s cross phi hat goes to z hat, and z cross phi hat goes to negative s hat. Okay, and then we're able to simplify down to A equal mu naught I over 2 pi s z s hat minus s z hat. Now, a little more discussion on this shows that the examples in C and D happen to be divergent lists, but this is not in general the case. For if we let L equal the integral 0 to 1 of lambda times the magnetic field that is of lambda r d lambda for short. We plug that in and we see that del, or the divergence of A, is equal to negative del dot r cross L. Okay, and then we can apply the product rule there. And we see that, again, we know that del cross r is 0 because the derivatives cancel them. So we're left with a negative negative r cross del cross, a negative negative, so we get a positive, r dotted with the curl of L. And the curl of L, we can compute that straight up through there by shoving the cross product to the magnetic field. And we see we got a little more math to do. And then we end up with the fact that we have del cross B, which gives us the current density from Maxwell's equations. All right, fair enough, simplify down. But we know that A is that the divergence of A is equal to mu naught r dot this integral that we just found. And we know that it vanishes in the regions where the current density is 0, which is why the examples in C and D are divergentless. But again, this construction shows that it's not always the divergentless. It depends on the current density. So to construct an explicit counterexample, we need the field at a point where J is not equal to 0. Say inside a wire with uniform current. Here, Ampere's law tells us that B of 2 pi s equals mu naught I enclosed, which is equal to J pi s squared, because of the cross-sectional area. So solve that through for B, and we get B equal mu naught J over 2 s phi hat. So plug that in to the integral we just found with the cross product and all that fancy jazz. And we see here that A equals mu naught Js over 6 Zs hat minus Sz hat. Plug that into the divergence form. Again, in cylindrical, it comes out with a couple extra factors, so be careful. And we see that it simplifies down to mu naught Jz over 3, which does not equal 0. Conclusion, the equation 2 does not automatically yield the divergence of A equals 0.